He has designed a variety of flood control projects, including dams and levees, and has additional experience stabilizing stream channels to prevent erosion and improve water quality. Additionally, he has served as a construction engineer of record and construction observer for a wide range of project types and sizes, helping owners and construction teams complete successful construction projects. Tonight, he will be presenting Texas A&M University Stormwater System Improvements Project, the Brazos Riverbank Slope Protection. With that, I'll hand it off to Chris.
Thank you. I think you got me here, but I don't...
Well, this is for the room, that's for the recording. So,
Oh.
But if you prefer to just speak loud, you
No,
don't
that's
have to
fine.
use the mic. So, yeah.
Thank you, Chris. As you said, I am Chris Larson with Stanley Consultants. I'm a geotechnical engineer, and this is a project that we had at Texas A&M University doing storm water system improvements, and a particular part of that project being a slope failure along the Brazos River that we installed, designed, and had a retaining wall constructed to protect a structure from like the progressing failure. Oh. The clicker doesn't seem to work. Perfect. So I'm going to go over the project background, the riverbank slope stability, instabilities, the design process, our construction, some post-construction photos, and then performance evaluation. As I said, this is a project for the Texas A&M University, which is located in College Station, Texas, which is kind of on the eastern half of Texas. And this project was kind of an overall storm system reboot for Texas A&M. They didn't really have any good stormwater infrastructure, so like whenever a large rain event occurred, it was kind of just uncontrolled. So we did detention basins, flow restrictors, stream channel protection, stormwater pipes, and a part of it was also doing the Brazos Riverbank slope protection, which will show up on the next slide here. So that's along the Brazos River. Next to White Creek is the creek that comes up from the Brazos toward the campus. And then this is the main Brazos River that's pretty far away from the campus, but they do have a wastewater treatment outfall from the campus that's in this area, so that's why it is related. These are some post-construction photos of the other features for the project. The leftmost being the detention basin and the flow restrictors that we designed and installed. Then on the right we have the channel stabilization and scour protection, and then some stormwater piping and features. The main feature for today, though, like I said, is they were having slope stability issues along the Brazos River that were approaching this house. And you might be saying, okay, it's a house, why is that related to the Texas A&M? They are a major donor from the university, and their wastewater treatment pipe does come out right here, so they kind of wanted to show, like, support or do something kind of for this homeowner, since they're such a big donor to the university. Common in this area along the riverbank with these soils is high flood events occur, and then they take out these sections of like soil in these U-shapes, and these tend to start slowly. You can kind of see it here along this riverbank where it's starting to fail, and then further downstream, more away from the house, there's this large slough that has occurred in about 2000. And this is an aerial image for 2014. But then in 2015, actually, they had another large failure that occurred in closer proximity to the house, within 100 feet, and that also took out their wastewater treatment outfall pipe. It's a little hard to see, but you can see the pieces of the pipe laying in this failed soil area. So we got contracted by Texas A&M to go out there, do an evaluation, come up with a design, and ultimately have it bid for construction, do a set of drawings to fix the problem. So this failure surface is about 10 feet, and you can see it is how close it is to this house and how it is continuing to move too by the cracks in the surface of the slough soil. So it is an unstable area that's not stable after it's failed. We were expecting it to progress up to 60 feet more or more. So we went through the whole project design process, from being contracted to doing subcontracts with Braun, with Jensen, I believe, to do the topo surveying. Then we did a residual strength analysis, which is of that slough soil, what's its shear strength parameters, so we could come up with a global stability model for a solution. Then we had an alternatives analysis, evaluating all the potential options from do nothing to doing more of a cutting back the slope or doing something more substantial with a retaining wall. And then from there, we did contract drawings, a contractor performance spec to design the wall. Hayward Baker ended up designing the wall. Construction, we had some construction observation site visits, and then ultimately the project was completed in 2018, I believe. So it's been performing for 7 years, so we'll eventually also look at its performance. We subcontracted Braun to do some soil borings both above the failure plane and within the failed soils. And you can tell pretty clearly that ST1, which is above the failure plane, is all undisturbed soils. ST2 was also logged as undisturbed. I think mostly because this section looks like it's still intact, but then this ST3 was all fill and all failed soils, with all of these being clay sands in the upper 15 feet or so, with fat clays underneath. And in this region, the Brazos River can flood frequently and suddenly, which leads to erosion problems with these fat clays and sandy clay soils, ultimately leading to these failure surfaces. Also, to get an understanding of how the failure is still moving, we installed 2 inclinometers, which just read the lateral displacement over a vertical distance. And we did those at one reading, an 8-week reading at ST1 and ST2. ST2 sheared off at 9 feet, so it was unusable, but it's obviously moving if it can shear off an inclinometer. ST1 was located above the failure plane and has a little bit of movement, so it's potentially still moving a little bit, but it overall seemed roughly stable, I would say. Then we also went with Gessner to do the topo and bathymetry surveying to come up with this contour map, which we then did a section across the failure plane toward the house, and it pretty prominently shows that same 10 feet sloughed soil surface that you can see in the same site visit photo. So from that, we are able to evaluate what we got and start coming up with solutions. So this is where we got into the residual strength evaluation and how do you determine the solution to protect this structure and the shear strength of the failed soil. So we did a few things here. This red profile graph is that same section shown here across this upstream failure surface, and this other profile is across this downstream failure surface, which has been going on for 10 more years. So we used that as a point of reference of if it's left unattended for an additional 10 years, we expected it to continue to a depth of about 212 and extend potentially another 100 feet beyond where it is currently, which would bring it in very close proximity to that house. So we wanted to do something, the university wanted to do something. Then we used GeoStudio to vary a soil layer that we are calling the residual layer to come up with our case soil parameters to determine like what are the residual soil shear strengths post failure in front of this block of undisturbed soil. So comparing these different thicknesses of the residual shear strength back to the inclinometer and soil boring results that we had, we ended up choosing 20 feet of residual soil thickness. That best matched the inclinometer data we had. So we felt pretty confident about that, because you could see thinner residual soil thickness ends up with a pretty shallow failure plane that doesn't match what actually occurred. Sending it significantly deeper seemed to do a much thicker soil failure area. So we weren't really thinking it was that. That's when we ended up with this 20-foot thick layer and this thickness of the residual strength. So all these figures here show the factor of safety of about 1 is this heat map plot. So everything in green or orange is below 1, everything outside of it is above 1, and we use that as a justification to select our residual strength parameters and the residual layer thickness. So after determining the design parameters we could use, we started coming up with a few alternative options. The first one, kind of as always, is to do nothing. It's not really the university's structure, so that is an option, but because, like I said, they're a big donor, they wanted to do something to protect both that structure and to help protect their wastewater treatment pipe that kind of comes in from the side and goes out in that failure area. So do nothing wasn't an option that they wanted to pursue. We also looked at stabilizing the slope either through cutting back the vertical failure surface or installing pile reinforcing to reinforce the slope at the toe. The pile reinforcing didn't really make it very far, as we just deemed it was too expensive and too difficult to install piles that it would be strong enough to retain such a large failure right off the river. This cutback slope option also was eliminated, more so because we were expecting the 60 feet that we would need to cut it back to get it a 3-to-1 slope beyond the failure point, and that kind of would take out all of their trees there that are back over here and kind of would just change the landowner's property. So they didn't, like the university didn't want to pursue that as an option. So the ones that we pursued further were installing a retaining wall to not allow the failure to progress closer to that building. There was 3 options that we looked at. Two of them are the same, one's a little bit different. One being the anchored sheet pile wall. The other similar one is an anchored soldier pile wall. And the third option was this open cell formation, which is essentially like cellular structures, but they're open on one side. They're not like fully contained. That option was just deemed too expensive and too complicated compared with the two sheet pile wall and the anchored soldier pile wall alternatives. So we pursued those two options, and we actually bid it as a contractor option for them to design their system. What we completed at Stanley was this preliminary design to prove its concept and that it would be stable in a global slope stability option and provide future protection to that house. So we completed another GeoStudio Slope W model, this time with the anchored retaining wall, that 20 feet of residual soil strength with some of it cut back, and our undisturbed soil layers. So we ran that in GeoStudio, that looked good. We completed an additional retaining wall analysis in Civil Tech Shoring Suite, which is able to do multi-anchored and anchored retaining walls and soldier pile walls designs. So that came up with a concept that one anchor could support this wall while allowing for future slope failures down to that elevation of 212 that I mentioned before. Because we wanted this wall to not just be unusable as soon as the slope continued to fail. From these two designs, or these two calculations, we came up with a drawing set with the rough alignment, a rough final grading plan to provide access for construction and to just clean up the slope a little bit. And the wall was ultimately bid as a contractor option, and Hayward Baker was the one that the prime contractor subbed to complete what ultimately was decided to be a soldier pile retaining wall. There was a little back and forth with them deciding between this and the anchored sheet pile wall, but with given the kind of the exposed face in our plan for the wall alignment, they ultimately agreed that a soldier pile wall was their best option. So they completed this wall design that has a 25-foot unbonded tieback with a 35-foot bonded tieback, all in soil, so it's a pure like soil tieback, nothing going into rock. I added this blue line being the soil wedge to show the unbonded length being extended beyond the soil wedge. This design elevation of 212 here, and then the existing and proposed grades showing where we're putting the wall in relation to that 10-foot sloughed soil face. So we did move the wall back a little bit to get it away from this failure plane. And this red line, which I'll address and talk about later, is where the ground is currently. So they kind of completed a little bit of a unique soldier pile wall design. It was actually two C channels with a gap in between that had the anchor and supporting plates mounted in that space between the two C channels. And instead of conventional like lagging, timber lagging, we added a concrete facing and a handrail that's shown over here, as this is a homeowner's property and we wanted to make sure there was no significant fall risk. There you go. So this is in the middle of the construction. They have all of these soldier piles driven, and these were encased in concrete. And then they have the first layer or lift of the concrete facing, the tie rods, tie backs installed with their nuts, drainage system behind the wall with the drains going through the wall. And this shows here the rebar going through those C channels I mentioned with the tie back in the middle of the C channel. And on this day, they were proof testing one of the anchors. These were 57 kip anchors that we tested to 150%, I believe, every anchor. This photo on the top right, I'll start with, is the pile cap or the wall cap before the handrails installed. And then this on the right is their excavation to gain access to installing that concrete facing down far enough to reach that 212 elevation. So everything on the right in all these photos is the failed soil surface that they cut back for access and to clean it up. This is relatively post-construction. You can see the wall is all in. We redid the grading up to those drains. Just for reference, those drains are right about those anchors. So there's like 7-8 feet below these anchors to the bottom of that concrete facing. And this shows the railing, the wall, the soil grading, and how it like transitions to either side where the wall tapers out. Since this was installed long enough ago, we have been able to go back to the site to complete some post-construction, just observations to see all the walls performing. So the slope failure did occur again after we regraded everything, pretty much on that same line as expected. This one's only 5 or less feet deep this time, and it did not go all the way to the wall face. So it's kind of just at that same slip surface interface where it originally failed. It's just following that same failure. And that was 2.5 years after construction. This is recently 6 years after construction. It's a little hard to see, but you can kind of make out the same failure plane coming across here. But now everything is heavily vegetated, so it doesn't seem to be moving very much. The vegetation is able to grow. And behind the wall, there's been really no change at all. So our wall does appear to be doing what we designed it to do. This slide I found particularly informative. So this is just a Google Earth timeline of everything that happened from before that first downstream failure to where we are today. So in 2023, or 2003 I should say, it's just a slight failure coming along the riverbank with a little bit of the downstream failure showing. 10 years later, that downstream failure has occurred, which matches almost what we were solving. In 2015, so a year after that, we had our failure that came across the wastewater treatment plant pipe and started threatening the house. This is the same year the wall was finished. So you can see the regraded, the road access, the retaining wall here in red coming across. And then the 3 years later, that first re-failure, I'll describe it, which matches the same failure plane as before. And then in 2025, it's moved a little bit toward the wall. It is very hard to tell though, but It seems like it has moved a little toward the wall, but it's still that same circular area with not much going beyond that. So, how did our wall do? We have looked at it again. We're still talking with the university about it. They've gone out there and taken a few photos for us. That's where we've gotten those post-construction site visit photos. The surface is moving in that same failure plane. I have the perimeter of that edge drawn in white with the wall in red here in the top right. So it has moved a little bit closer to the wall. It is very hard to tell though, in just the Google Earth imagery without doing like another topo of the site. The area is heavily vegetated. The failure is still above that 212 that we had as a limit to the retaining wall design. And the failure plane is still matching what was there before and what we were expecting out of both looking at this surface and evaluating that downstream surface. For the retaining wall itself, so wall isn't moving, the ground hasn't exposed these anchors, the tops of the anchors yet, and it does appear to be adding protection to that homeowner. I will say the wastewater treatment pipe was relocated, and while that wasn't a focus of this presentation, it has slightly shifted as it was left on this failure surface. So that is like a future problem or a challenge that we plan on going over the university with. But for future considerations, we are still in discussions with the university. We have a new project with them, so we will be continuing to monitor this failure surface, and from like mainly visual, unless something shows itself, then we can engage additional investigations again. So they plan on regularly checking in on it. We'll remind them as needed, since this is not very close to their main facilities. And we just have a continued partnership with the university to do additional storm sewer improvements and correcting this remaining issue with the wastewater treatment pipe coming out here on this left side of the wall. So that was a quick overview and like breakdown of that wall design and its performance evaluation. Thank you for having me, and I'll just open up to any questions you may have. I think it's Chris in the back. Eric, oh, I'm sorry.
I had a question. It looks like you did some soil boring.
Yep.
The failure surface went through the fat clay.
The failure surface went through the fat clay, correct.
Can you talk a little bit about the additives and links in the last testing we did concerning the residual strength? I assume that you were, it looked like that.
Yes, there is some, and there is a change. I believe it's here on this left one, if I get a little closer.
I just can't see the screen.
Yeah, so they're like at this like 15 feet, there is a change. Predominantly, you can see it in the cheer, the QP. So it changes from about 125, 275 to this 4 below. And then everything on this side is also 4 below. So that matches up with what we were saying from our group, or not a group model, our slope stability model, and roughly. I'm a little unfamiliar, so I had to look at it too. So up here we have a 33, a 36, and then it drops down to a 25, 26 below. And then over here, it's 20, 22, and there's a 32 in this fat clay down below.
Residual strength testing from your back analysis?
No, not on this one.
Thank you.
Two questions. What development limits did you guys give to the homeowner and the water treatment plant? Building a wall right up against the backyard. Did they have, like, you can't excavate 5 feet, more than 5 feet of soil? Was there anything basically given to the client and homeowner about the development limits?
That wasn't particularly discussed. Their main concern was,
Like, if they wanted to put a swimming pool out in the backyard and they all dug a 10-foot hole with that remove the factor of safety and
it's a good point, that was not discussed. What they're primarily worried about is more like our impacts to them. I was trying to find a photo of it. It's right here. So there's a tree right along, very close to that failure plane with more trees behind it, further back. So it was a discussion point, is there a way we could save that tree, which eventually was like, no, its root ball is exposed, it's right there. We said the tree's got to go. But as for like restrictions on the homeowner to like change anything in their yard, that wasn't discussed with them at the time. Yeah, if they did something like, yeah. Yeah.
And then a sister question to that was, is the service life on your wall shorter because the soil, the flooding events are so uncertain, like they happen much more often? Like you couldn't say this is a 100-year wall just because of how often the river floods?
Yes. Yeah, there is a little uncertainty with, 15 years from now, are these two failure planes going to connect? That's why we tried to have this little wing here to prevent it from creeping around, but yeah, it's not a 100-year design life.
I guess maybe a little easier question. If this was a retaining wall in a place that didn't flood, it was just you were trying to hold some soil back, I got it a wall, would this be half the life of that one? That was never something flooding?
Yeah.
So there's two planes there, and you talked about them maybe merging. Are you actually still observing the second one too? Or will you see it progress further back?
Yeah, it has moved a little bit. It's a little hard to see, but this one is longer in its distance between the river and like its back than this one was in 2016. But it has not moved significantly beyond that. But there's also a row of trees right there too that could be holding it back. Between that and like as another larger flood event occurred to make additional failures happen, it seems to be a little bit, and then like a larger event occurs and then it takes out a lot. It's further downstream, there is a community, I would say, that's pretty close to the riverbank, and they had to go fill in a bunch in the river to stop their like houses from being taken out from a similar thing of a little bit, and then one year a larger flood occurs, takes out like almost right to their houses. I don't know like who filled it in, but in the aerial imagery you can go see that it's somebody came in and filled in all of the riverbank to protect them. Jason, you said you were going to have a question.
I got all kinds of questions.
Yes, Chris.
So you mentioned that you're currently looking at there's a wastewater pipe going along that's like, I guess outside the scope of this, but it is sort of related. That one of the other places is cutting through a wastewater pipe, and you're going to have to address that.
Yes.
I'm assuming the main concern there is like, if it's far enough wastewater pipe to break.
Yeah, so it's the same thing that happened originally where the pipe was coming across, the original pipe came across the face of the wall and exited down here. When this failed, it took out like the middle of the pipe. This blue is a temporary thing the university just like put in an emergency situation. They, in our contract, like in design plans, relocated it and attempted to stabilize it with some riprap, which isn't like an ideal way to stabilize it in a moving soil. So it has separated a little bit down here at one of the collars between the pipes. And then that's, yeah, it's outside this specific thing, but it's going to be a larger thing that we try to tackle with the university.
Okay, thank you.
If there's nothing else,
What was the total cost?
I don't have that information, unfortunately, because we're a little we're removed from that, both for this and for that. When we estimated it, I believe we estimated it at $4 million. Yeah.
Assuming the donor gives more than that.
I would hope so. I assume so. I also don't know how much they give, but from everything they've said, it sounds like it's very substantial.
All right, then let's give a final round of applause.
Thank you.
We do have PE agents.
Want that? The keeper?